Hello, listeners. Welcome once again to this favorite channel of physics. Today, we are looking at a very important part of refraction of light wave, that is, a consequence of refraction of light wave. So, let's see. Now, the consequences of refraction of light wave. Basically, on screen right now, we have three consequences of refraction of light wave stated. One of them is the apparent bending of a stick in water. That stick could be a rod. The second one is the bringing of objects into view. The third one there is the apparent depth of a swimming pool when viewed by an observer at a distance from the swimming pool. Usually the observer sees the swimming pool to be nearer or shallower than it actually is. That means the depth appears to be shallower. Why? This concept will be studied in the next video or perhaps subsequent videos. Now, we want to look at the first one clearly, and that is the apparent uh, bending of a stick. Okay, very important for the exam class. Here we have the apparent bending of a stick. Now, you can see a stick in this one now. You can see the stick right now, the solid lines inside water. Alright, the bowl contains water. Now this stick, when immersed the water, an observer at point P will see the stick to be bent. Why? This is the result of refraction of light. When light ray from a point underneath the water from the stick at point O precisely travel from water outwardly on reaching the water-air boundary or interface, the ray of light will bend from its actual course and follow this path to the eyes of the observer. If we take another ray of light from the same source or the same point O or near O, and we project that ray outwardly on reaching the interface separating air and water, that ray will also bend away. So we can use these two rays of light to determine the image of the object that will be formed. Now, when these rays of light are bent actually from the actual path, and we project the rays back into the water, now the two rays will intersect at some point I. The point where the two rays that actually emanated from the water intersect backwardly inside the water, at that point an image of the object will be formed, that is at point I. When this happens, the observer now sees the object to be at the end of the object, which is actually point O, to be at point I. That is not actually true. It's an image of the object that is formed at point I due to refraction of light. Now, when this happens, every other point of the stick that is inside the water, for instance, this point, this point, this point, along this path inside the water, we have an image formed along I also until perhaps outside the water region, where I just link up with the original stick outside the water region. So the observers at point P, we see the stick to be in this position part I, or along part I rather, which joins the actual stick outside the water, and so the image of this side will appear to be bent because the image is joining the stick outwardly is not straight. So the observer sees the stick as being bent under water. This is a phenomenon due to refraction of light. So I believe you understand clearly. So from the concept of refraction, you can see this clearly. I repeat it, the ray gets to this point, bend away from its actual path. That means bend away from the normal. This same thing will happen here. And the two rays that bend out will project backward and intersect at some point are inside the medium that the light actually came from, which is water. And when this happens, you see this ray of light that have intersected here will continue to form other rays at different points from the same stick, forming an image that will link with that actual object outside, and then the object now appears bent in the eyes of the observer. So that is for the refraction of light phenomenon that has to do with the bending of a stick when partially immersed in water or any other liquid, precisely transparent liquid. So this is a very important concept. I hope the learner understand this. Now, the real depth and the apparent depth. Now, the real depth is a phenomenon that happens, okay, based on the last description, but precisely refraction of light. Now, what do we mean by real depth? As in the case of the swimming pool that I tried to explain briefly with our diagram, an object actually will appear when viewed from the top will certainly appear to be closer to the surface. Why? For instance, an object that is kept underwater or any other transparent medium different from air, when viewed from air above, you can see that object to be closer to air or to the boundary face separating air and the medium where the object is kept. Alright, this is as a result of refraction of light, and this concept is a very important concept because it will give rise to a formula for calculating refractive index too, in case we are not concerned with the speed of the wave or light wave in the medium. Alright, we can use the concept of real depth and apparent depth. So, as you can see on screen, when an object is viewed from the top portion of a transparent medium, such as glass for instance, you view it on top, that is in air, you view this object. Alright. The object tends to appear nearer to the surface than it actually is. Okay. And this is as a result of refraction of light. Now, light travel from the object in the medium where the object is kept. On reaching the interface separating that medium, say for instance glass or liquid that is transparent, let's say water, the ray of light will bend away from its actual course. That means it will be refracted. And when it happens, an image of this object that is being viewed will be formed, alright, by the two or more rays, whatever, that the observer sees. Now, this image will be formed inside the medium where the light or ray actually came from, but they will actually intersect at a point rather closer to the eyes or nearer the surface or interface separating that medium and air. And so the observer sees the object to be closer to the interface or surface separating the medium and air. So therefore, since the object's image is closer to the surface separating the medium and air, that means the object's image has a distance from the boundary interface or surface separating the medium and air that is not true. That interface is called that distance rather from which the object's image is formed to the interface. That distance is called the apparent depth. As you can see on screen now, the distance the object's image is seen as as the object and tend to emerge from a nearer position to the what eyes. Now, therefore, as you can also see on screen, the distance between the object and the top surface of the medium is known as the ray depth. So that is the object's original position, that is the ray object. The distance between the position of the object and the top surface is called the ray depth. As you can see in this diagram, all right, you can see from here down up to this point is the height of this glass block, and this object, say a pin placed at point O, okay, under the glass, has a distance from its position O to the top point of the glass where the light is refracted. The top point of the glass is the layer or interface or boundary face separating glass and what air. So that distance from the top surface to the base where the object is, for instance, at point O, that distance is called the ray distance, as you can see here. So back now we see that also there's a distance that is between the object image and the top surface. There's a distance between the object image and the top surface. That distance is known as the apparent depth. Now, the gap between the apparent depth and the real depth is known as the apparent displacement. Let's see this. Now, back again to this diagram, you can see that a ray of light from O will form an image at position I due to refraction. So a rays of light, not a ray, will form an image at position I, not at this point, sorry, at position I, and then I is closer to the boundary interface separating the medium where the object at O is. So the image at I is closer to the top surface. As you can see, this is the top surface or the layer separating air, which is this is air now, and the boundary or interface between glass and air in this case, since this one is a glass block. Alright, now the distance between the image at I and the top surface, alright, that distance is called the apparent depth, as you can see on screen here, apparent depth. Therefore, the gap between the sorry for that each, the gap between the apparent depth and the base where the object is, that means the gap between I where the image position and O, that gap is known as the displacement. That means the object appears to be displaced from position I to position sorry, from position O to position I as a result of refraction, but that's not true. The object is actually still at position I, just the image of the object that is formed at I as a result of refraction of light. So how is this formed, or how does this happen, or how did this happen? Let's see. Now, a ray of light travel from point O, position O rather, and travel to the boundary face, and then on reaching that point, bends away from its actual course. Look at this, and in air it appears to be broken, the broken lines you can see. Another ray from the same point, okay, at the same on the same point, will travel, and on reaching the surface or interface will bend again, as you can see the other broken lines. If we combine these two emerging rays from the medium, that means the glass, that were bent or refracted, the two, and project them backward so that they combine and meet at a point inside the medium where the original light ray, this ones, came from. The two refracted rays will appear to meet at this point and projected backward, okay, and when they meet at this point they form an image at this point. Likewise, rays from other portion of the object will do so and then form a complete image of that object at level I. Thus, an image of object O or object at O is formed at I. That is how refraction of light forms It forms image of object on the object placed in one medium and viewed in another medium. So I believe you understand this concept. So as simple as it is, learners should be able to explain this. So to cap it up or to summarize, suppose a ray of light is taken from point O and the ray travels from medium 1, which is glass, on reaching the boundary phase separating air glass, it bends away to from the normal. Another ray of light from near that same point or at the same point travels on reaching the same boundary phase, also bends. The two rays combine straight, or the two rays projected backward will intersect and form an image at I, and so the object image is formed at I. That's a simple explanation which can be written by a student in any exam to explain how objects' image are formed due to refraction of light inside a given medium, and hence the object appears to be closer to the boundary face than the object image rather appears to be closer to the boundary face than the object itself. This will give rise to a calculation. That means we now need to calculate the refractive index between the pair of say air and glass in this case. Now, the refractive index of a medium can also be given in terms of ray depth. We have already seen in previous video, alright, that refractive index is the speed of light in medium 1 to the speed of light in medium 2. Where medium 1 is the medium where light actually came from, okay, and then move into medium 2. Or perhaps the angle which the light makes with the normal in the first medium, which is the angle of incidence, and the angle which the light makes with the normal in the second medium, that is the angle of refraction. When we take the signs of these angles, we can use that to determine the refractive index. But that is not the case. Those are not the case now. Rather, we are looking at the position of the object in the medium and its image in the same medium. Alright, how they stand from the boundary face between a pair of media. So therefore, we cannot say the refractive index without proof is the ray depth divided by the apparent depth, or simply the ratio of the ray depth to the apparent depth. So let us use this to solve with just an example. Now, a fish inside a pond appears to be at a depth of 1.5 meters. When viewed vertically from above, the refractive index of the water in the pond is 1.3. Take note of that. Calculate the apparent displacement of the fish. Take note of that. They did not say apparent depth, but apparent displacement. So you can see clearly in this example, the pond appears to be at a depth of 1.5. That appears means that's not the true depth, meaning that is the apparent depth. So bear in mind the apparent depth is 1.5. Now, the refractive index of the medium is given as 1.3. So that means we don't know the ray depth, and they want us to find the apparent displacement or simply the displacement. So what do? We need to find the ray depth first. Now, the refractive index is equal to 1.3. The ray depth is unknown, as you can see the question mark there. The apparent depth is 1.5 stated in the example. The apparent displacement is what they want us to find. We do not know it. So therefore, refractive index is the ray depth over apparent depth as quoted before. And so we substitute values of 1.3 in place of the refractive index n given and 1.5 in place of the apparent depth. We arrive at the ray depth is equal to 1.5 times 1.3. And the ray depth is therefore, after cross multiplying 1.5 and 1.3, we have this on a straight line here. And so the ray depth is 1.9 after multiplying that value, those values rather. Now the apparent displacement therefore is given as follows. The apparent displacement is the apparent depth equal to real depth, or in a different way, the apparent displacement is equal to the real depth minus the apparent depth rather. The real depth minus the apparent depth will give us the apparent displacement. So therefore we have to subtract the apparent depth which was given as 1.5. When we do the subtraction, we are going to add 0.45. Both units are all units are already in meters, so we just attach m meters to the calculation and that sums it up. So here we are. We have a we have questions rather. These are questions for learners to solve, and the solutions of these will be presented again, so the learner can confirm his answers or answers with the solution that will be presented in the next video. So do well to solve these questions so that you get ready for your exam and then compare with the answer to be rest assured that what you have done is correct. So you also need to look at this one. It's a very good question too. Don't just pick any option there. Make sure you determine it by working things out. So give this video a thumbs up if you really got something from it. See you next time. Bye for now.